Welcome to This Explainer. Today we're diving headfirst into what might just be the ultimate astrophysical puzzle, Caldwell 79. Look, we're going to jump right into this, because what we have on our hands is a stellar mystery that has literally had astronomers arguing for decades. It's a system that fundamentally challenges our definitions of how galaxies and star clusters even form. So let's kick things off with a pretty provocative question. Could this seemingly quiet little cluster actually be an alien invader, like the captured nucleus of a dwarf galaxy from way beyond our Milky Way? I know it sounds completely like science fiction, right? But as you'll see from the data we're about to look at, the clues pointing to an extragalactic origin are just incredibly compelling. Section 1. Meet Caldwell 79, a globular cluster in the Vela constellation. To really understand this mystery, we first need to get acquainted with our cosmic suspect, which is located deep in the southern sky. Let's check out the vital stats, because these numbers show us exactly why astronomers are so suspicious. Okay, so it's sitting 14,800 light years away and is estimated to be incredibly old, between 11.5 and 12.2 billion years. It's classified as an Osterhoff type 1 cluster, which is a specific category known for its pulsating stars. But you know what the real red flag is? It is absolutely screaming through space on an extreme retrograde orbit. Basically, it's moving backward compared to the general flow of our Milky Way, clocking a radial velocity of negative 494.4 kilometers per second. Honestly, that alone raises massive questions about where this thing came from. Moving on to Section 2, a chaotic stellar graveyard, the cast of characters. Before we get into the main controversy, we've got to zoom in on the cluster's inhabitants, because inside this fast-moving system, things are anything but peaceful. You see, Caldwell 79 isn't just some quiet retirement community for old stars. It's way more like a chaotic cosmic reality show. We've got over 86 RR Lyrae variable stars, which ties right back into that Osterhoff type I classification we just mentioned. Plus, there are at least 24 short-period SX Finis stars. We're talking complex detached eclipsing and contact binary systems, rare sub-subgiants emitting X-rays, and, my favorite part, beneath it all, a dark core. Simulations actually suggest this non-core collapse center is hiding a subsystem of anywhere from 100 to 200 stellar mass black holes. Now, take a look at this number, a staggering 57.5%. What's so interesting about this is that it represents the massive percentage of core blue straggler stars found in binary systems here. And blue stragglers are just fascinating objects. They are these massive, bright stars that look way, way younger than the ancient 12-billion-year-old cluster they actually live in. Because of how violently crowded this core is, these stars are literally forced to crash together, or kind of empirically steal mass from one another, just to appear artificially young. So yeah, formed through mass transfer or stellar collisions. It's a highly dynamic and, frankly, dangerous neighborhood. Section 3. The Iron Abundance Controversy. The Core Conflict. This brings us to the real heart of this explainer, which is a heated, decades-long scientific debate over the cluster's chemical makeup. If that extreme retrograde orbit didn't convince you this cluster was strange, well, its chemistry definitely will. Before we dive into the debate, we really need to understand this term, monometallic. For a very long time, the golden rule for your typical globular cluster was that it had to be monometallic. This basically means the whole cluster formed all at once, from the exact same uniform cloud of gas. Because of that, every single star inside the cluster should share a uniform, homogeneous iron abundance. They should all have the exact same baseline level of iron. But as this timeline shows, astronomers have essentially been playing a cosmic game of ping pong over whether Caldwell 79 actually follows this rule. Back in 1998, researchers Gonzalez and Wallerstein reported a massive 0.4 dex spread in iron. Now, in astronomy, that's a logarithmic scale, so a 0.4 dex spread means some stars had vastly more iron than others. Fast forward to 2009, a larger study analyzes 162 stars and finds only a tiny 0.05 dex spread, arguing, hey, it's monometallic, perfectly normal. Then in 2013, boom, the 0.4 dex spread is reported again, only for a 2018 study to jump back in and firmly state, nope, the cluster is totally homogeneous. Talk about whiplash. Looking right at the physical evidence, the studies arguing for that massive iron spread point to exact spectral lines, just like we're seeing here. We're looking at direct comparisons between stars that have very similar temperatures. Those deep dips, those are iron absorption lines. Now, if the stars are the same temperature and they're from a monometallic cluster, those lines should overlap perfectly. They should be identical. But as you can clearly see, one star has consistently stronger iron lines across the board. For a lot of astronomers, this is it. This is the smoking gun, hard physical proof of an iron spread. Section 4. Two sides of the debate, unpacking the methodology. So how on earth can some of the brightest minds in astrophysics look at the exact same cluster and arrive at completely contradictory conclusions? Well, it all comes down to the tools they're using. The absolute root of the disagreement is the diagnostic method. Think of it like this. If researchers estimate a star's temperature using spectroscopic diagnostics, so looking at those spectral lines, the cluster looks highly anomalous. You see that large 0.4 dex iron spread. But if you take those exact same stars and estimate their temperatures using photometric diagnostics, meaning you look at stellar colors and brightness instead, the temperature estimates shift. And just like that, the massive iron spread vanishes entirely, making the cluster look completely normal. And this brings us to the big counterargument. A lot of researchers argue that the so-called iron spread is actually just an illusion. They think it's a mathematical ghost caused by failing to account for something called NLTE effects, non-local thermodynamic equilibrium. Basically, these are incredibly complex atmospheric artifacts. The argument goes that if you don't perfectly model the intense, complicated physics happening in the outer atmosphere of these specific stars, the spectroscopic data will flat out trick you. It'll falsely create the illusion of varying iron abundances that just aren't really there. Section 5. Breaking the cosmic dichotomy. The plot twist. Okay, but here's the thing. Even if we assume the iron controversy is just an illusion, and Caldwell 79 really is monometallic, the cluster still refuses to play by the rules. We've got a massive plot twist in the chemical data. What we're looking at now is called a chromosome map. It's a really cool tool used to map a cluster's chemical DNA, but instead of looking at heavy metals like iron, we're looking at light elements. And this map provides concrete visual proof of an anomaly in Caldwell 79. It clearly displays multiple distinct groupings of light elements, effectively separating the cluster into first and second generation stars based on some massive chemical differences. Specifically, astronomers found 3 distinct sequences of this carbon-nitrogen, carbon-hydrogen anticorrelation. So you've got one group that is carbon-rich and nitrogen-poor, and then another group that is exactly the opposite. Now, finding 3 distinct sequences like this is a feature usually reserved strictly for anomalous clusters, the really massive ones that definitively have real iron spreads. Yet, here we are, seeing it in Caldwell 79, which has scientists completely baffled. Section 6. The grand implication, rewriting the rules of galaxy formation. Let's start tying all these clues together, because this data, it doesn't just describe one weird cluster. It genuinely challenges our broader models of the universe. So, what is the final verdict here? Well, if that 0.4 dex iron spread is real, Caldwell 79 is a highly anomalous cluster. Combine that with its extreme retrograde orbit, and it strongly supports the theory that this is actually the captured, stripped-down nucleus of an alien dwarf galaxy that merged with our Milky Way a very long time ago. But on the flip side, if the photometric camp is right and the iron spread is just an illusion, then Caldwell 79 is the very first monometallic, non-anomalous cluster to possess multiple CNCH groups. Either way you slice it, the strict dichotomy astronomers used to divide typical and anomalous clusters is completely broken. Caldwell 79 forces us to fundamentally rethink how stellar systems form. I'm going to leave you with this thought to ponder. If a seemingly minor chemical debate can rewrite the rules of galaxy formation, what other cosmic secrets are hiding in plain sight? Seriously, if we can find this much mystery, alien invaders, dark black hole cores, and rule-breaking chemistry hidden just in the spectral lines of one single cluster in the Vela constellation, just imagine what else is waiting to be discovered up there. Thanks for joining me on this deep dive for today's explainer. Keep looking up, and as always, keep questioning the data.